about Newton's theory of gravitation, Einstein's theory of general relativity, and you know that when you have a mass, this mass influences the space-time curvature in a way that it attracts other masses. So if you have two masses, these are going to be attracted towards each other. So if I put some particles in space, which has a certain mass, they're going to try and come together because of this gravitational attraction, right? So matter will start clumping and forming huge structures, bigger and bigger masses, right? But then why is the universe not just one big whole mass, right? If that is the only force in the universe, then you would have this one big thing, right? Not this small little planets, multiple stars and galaxies that you see. So what's stopping it? What stops is pressure. So once you start clumping matter together, the internal part of this matter starts getting heated up. And then when the temperature is very hot, you suddenly ignite nuclear reactions, which is known as nuclear fusion. And this generates a lot of energy, which increases the temperature in the interior of this matter and therefore increases the pressure. Now, the pressure likes to push particles away, right? So gravity is attracting and trying to clump together material, whereas pressure is trying to hold and push together, push out the matter. Eventually, a balance is achieved. And when the gravitational forces are balanced by this outward pressure gradient, a stable star is born. And what you see here is an observation of the large Magellanic cloud. This cloud is essentially a distribution of interstellar gas far away in the universe, imaged here with the Hubble Space Telescope. And in this cloud, you see this cooler material, which is denoted in this brown color, but you also see this really bright stars. So these really bright stars are the star-forming regions where young stars have just formed. So essentially what you're seeing is a nursery of stars where stars are being born. So our sun was born in such a way, in a nursery of stars. Okay, how does a star become stable? Why doesn't it collapse under gravity, and what holds it together for so long? I mean, the Earth has existed for 4.5 billion years, so has the solar system. Human beings, intelligent life forms have evolved over multiple eons. How does this work? What gives this long time scale to stars and stellar systems? Where it comes from is the ability to have nuclear fusion reactions, which can produce energy to form a stable star. Well, forming a hydrogen atom is not so difficult because you have a proton, which is got a positive charge, and then you have an electron, which has got a negative charge in orbit around it. That's the hydrogen atom. And unlike charges or opposite charges attract each other. So this is fine. But then imagine how do you fuse this nuclei of atoms to produce higher mass elements like helium, right? To do that, you have to bring another proton into the nucleus or the center of the atom. Now, because protons are positively charged, if there is one positive proton sitting in the center, when you try to bring another positive proton, they are going to try to repel each other. That's the Coulomb force, which is repelling the two protons, right? So to overcome what we call the Coulomb barrier. So imagine that you have a potential barrier, which is an energy barrier, and this energy barrier has to be overcome by an approaching proton to come to the nuclei and join with this other proton which is sitting here to form a higher mass, higher atomic number nuclei, right? So how to achieve that? You can only achieve that if the energy of the approaching proton is higher than this potential barrier, at least in the classical picture. Okay, so what it implies is that this approaching proton has to have very high energy, kinetic energy, which is only possible if it is in a gas which has a very high temperature. And when you have a high pressure, this really facilitates this because you're squeezing together the particles anyway. And there is this other effect called quantum tunneling, which depends on temperature, which also helps the proton tunnel through this barrier and approach this proton. All of this requires very extreme conditions of temperature and pressure, which is only achieved in the interior of stars. And when you fuse this atoms together to produce a higher mass element, you lose some mass, and that mass deficit is converted to energy. And you may recall Einstein's famous equation E is equal to mc squared. So that mass deficit there is converted to energy, and this is how nuclear fusion reactions produce energy in the interior of stars, which holds the star against gravitational collapse. And that is exactly how a stable star like the sun is born. And around it, a protoplanetary disk forms from which gravitational instability starts forming smaller planets. The material in the planets are not enough to start fusing atoms in its interior. So nuclear fusion reactions do not happen in the interior of planets. It happens only in the stars. And the planets start orbiting around the star. And therefore, this is the way that our solar system was born, the star, our sun was born, and the earth was born. So when you look at the interior of the sun, the hydrogen fusion, which creates helium, happens right at the center where the conditions are most extreme, where the temperatures can reach something like 14 million degrees Kelvin. That's extremely, extremely high. Okay. So from there, the energy is first transported by radiation or moving photons, and then through convection. Convection is literally the up and down motion of gases, which are transporting this energy. And when energy reaches the sun's surface, it radiates. And that's how you see the sun as a very bright star whose radiation sustains life on Earth. So I will talk about how stars will eventually die, how stars of the sun will eventually die. But there is a very interesting thing that I want to talk about. When you have a star which is much more massive, much bigger than the sun, eventually when they lose the nuclear fuel which is powering them, it collapses, and there is an explosive phenomenon known as a supernova explosion, which results in a shock wave that travels through space. And this is very important because, within these massive stars and in the supernova explosions, much more higher mass elements like carbon, nitrogen, oxygen, iodine are born. And these are very important elements because they actually form planetary crust, they form the atmosphere of planets, and they also constitute the cells and structure of living beings, whether primordial life forms or even human beings. And therefore, when such massive stars die, these elements which have been cooked up in their interior is spewed out by these supernova explosions into space, and it gets mixed up in interstellar gas. And when a new system is born from this, all the elements that is necessary for forming an atmosphere like that of planet and forming the structure of life forms and human beings is there, and you can draw from it. And therefore, it is often said that we are made of star stuff. In fact, when you look at the periodic table, the secret behind the periodic table that many of you would have seen in chemistry is that most of the elements, in fact, all of the elements have been cooked up either in the interior of stars like the sun or much more massive stars, or in supernova explosions. The lightest elements like hydrogen, helium exist from primordial nucleosynthesis or in the very early universe. But then all the other elements that is very important for us has really been churned out and cooked, if you will, in the interior of stars. And when they die, this is distributed in the universe. And from there, when new stellar systems are born, we have all the ingredients for forming planets, their atmospheres, and in fact, life. And Carl Sagan, whose birthday was just a couple of days back on 9th November, outstanding science communicator, said, "The cosmos is within us. We are made of star stuff." And this is exactly why he said it. Okay, let's now get back to the sun and look at what the sun does for our space environment. So the sun is not a benign star. When you look at the sun, All we see from Earth is that it rises in the east and then sets in the west. And at best, there is a change in color, which is not really due to the sun, but due to scattering in the Earth's atmosphere. You don't see anything else. And it seems to you that the sun is just an unchanging, hot star that is bright and nothing else is going on. That is completely untrue. What you see here is a satellite observation by the Japanese satellite Hinode, which means sunrise, of, of extremely energetic events known as solar flares on the sun. So what you see here is this dark region is a magnetized sunspot. These are known as sunspots. And sometimes the magnetic fields gets destabilized and gives rise to this massive storms. Each of the storm has the energy equivalent of something like 1 billion atom bombs bursting together. Understand that. 10 to the power 9 billion atom bombs bursting together. That's the amount of energy each of the storms contain. And they can, in principle, go in every direction, but sometimes they're out directed. Now, the sun also produces a lot of high energy radiation that thankfully is cut off by the Earth's upper atmosphere. It absorbs it. This radiation in extreme ultraviolet and X-rays actually impact the Earth's upper atmosphere, hits it up. The sun also spews out high energy particles, which travel close to the speed of light, and they can impact our space environment and satellites. And you see that here. You see this shower of high energy particles, which is accompanying a solar storm. And this is impacting the siccity of a satellite. And you see this image here. It's almost like a shower of particles here. And these are extremely dangerous for satellites and the health of astronauts who could be out on a spacewalk. So you need to be able to forecast these storms to be able to protect the satellites and astronauts who are, and schedule spacewalks by astronauts who are in the International Space Station. The solar storms and the plasma winds from the sun, when they interact with the Earth's upper atmosphere, especially at the polar regions, also create these beautiful auroras. What you see here is aurora borealis, or the northern lights. This really happens because these energetic particles from the solar wind and the solar magnetic storms come through the Earth's atmosphere and impact the particles in the upper atmosphere of the Earth, energizing them. And when they come back to the ground state, they emit a photon. And the frequency of that photon, or the wavelength of it, depends on what atom it is. And depending on that frequency, it can emit in different possible lights. And you have this beautiful phenomena, which is known as northern lights, that you again see because of the interactions of solar activity with the Earth's atmosphere. Now, this is important to realize that the sun, in fact, impacts each of us, including you, even though you do not know it. When you have a solar storm, because it can disrupt satellite functioning and your cell phone communication, your towers communicates via satellites within one part of the country to other parts of the country as well as the world. Your GPS navigational networks depends very sensitively on a suite of satellites, which basically powers the global positioning system. That navigational network is prone to errors when there's solar storms. Solar storms can take down electric power grids in high latitude countries. And in fact, in 1989, a big solar storm took down a large part of the North American power grid, and Quebec and the city of Montreal was without power for a couple of days. When you have solar storms, it also impacts sensitive instruments on flights over polar routes. And therefore, when you have a flight going over a polar region, and polar region flights are important because it cuts down the travel distance. Let's say between New Delhi and New York, you want to go over the poles. So you require less fuel when you're going over the poles, but the poles are most prone to this space weather generated by the activity of the sun. So all of this depends on the availability of accurate space weather forecasting. We heard about climate a little bit in the introduction of today's talk. That it's been an important year for grappling with a changing climate and what different governments are doing by coming together to help mitigate. the impact of global warming. So, what has the sun got to do with with the climate? Well, so what is known is this, that there is a cycle of sunspots, and what you see here on the background is this sort of, on the y-axis is the amplitude of the sunspot cycle, on the x-axis is time, and you see this up and down sort of curve, which means it's a cyclic process. The magnetic activity of the sun increases and decreases in a cyclic fashion. But between 1645 and 1715 AD, this magnetic activity of the sun almost disappeared. There were no sunspots seen. And during this time, we also know that Europe went through the most severest part of its sort of a global cooling phenomenon known as the Little Ice Age. And what you see here is a painting of a river from near Amsterdam. And you see that the river has completely frozen, and there are people who are walking over on the river. And this doesn't happen normally. Okay, rivers in near Amsterdam in England, they don't freeze. But during this period of the Little Ice Age, which coincided with this minimum in solar activity known as the Maunder minimum, these rivers froze and temperatures plunged. The question is there a direct connection between climate and solar activity? Okay, so if you look at the amount of energy that is coming out of the sun, it has a name, it's called solar, it's to be named solar luminosity, and also called the solar constant, unfortunately, for a long time. It turns out it is not a constant. So we now have, since the 1978, measurement of the energy output of the sun arriving near Earth per unit area per unit time, and that plot is here. And we again see a sort of up and down modulation of this energy output from the sun, which is incident on Earth. And surprisingly, that is completely correlated with the number of sunspots or the solar magnetic activity that you see. When there are higher number of sunspots or stronger magnetic activity, the solar radiation is stronger. When there are lower number of sunspots, the solar radiation is in fact lower. Okay. Now it's important to realize that the sun's energy output is very strong. In half an hour, the sun provides enough energy to sustain all the annual needs of humanity. Whatever activities we are doing, if we could harness the solar energy completely, in half an hour, it could provide enough energy to sustain the needs. Of course, that is, we are not yet there, we can't do it, but therefore solar energy is a very active area for such. Okay. But the point I want to drive home through these plots is that the solar energy output is not a constant, it varies. And this is the primary energy input into the climate system. And therefore, you'd expect that there would be a solar influence on the climate. Now, how is that influence? Okay, so to do that, we really need to reconstruct past solar activity and past global temperature records. And there are ways to do that. And I will not go into the technicalities, but what you see here, here is time on the x-axis and the temperature, global temperature anomaly in this blue curve. This blue curve is the global temperature anomaly. And the red curve here is the sunspot record. You just look at these two plots, and it gives you an impression that in the past, the two curves, the global temperature record as well as the sunspot activity or solar activity, seems to have been following each other. And there seems to be a correlation between them. And over the last 100 years, solar activity has increased. So has the global temperature. But you should not get fooled just by two curves, because correlation does not always imply causation. It doesn't imply causality, doesn't imply there is a direct connection necessarily. To understand that, to appreciate that, you have to explore the physics of it and do more. Okay. So by looking at this curve, you get a hint and you ask yourself this question: is sun behind the global warming that we have seen in the last 100 years? Okay, and this is something that has resulted in a large-scale, massive activity over decades through the Intergovernmental Panel on Climate Change, the IPCC, who have looked at this phenomena. Based on research which resulted in this year's Nobel Prize in Physics to Manabe and Hasselmann. Okay, and what do they find? So what they find is this. If you perform a computational theoretical model of, of the change in global temperature with only natural sources of energy like the sun and volcanoes, then what you get is this blue curve. Okay, with time, you see this blue curve. Now, when you build a physical model where you not only have the natural forcing, but you also include the forcing that the observed temperature record beautifully matches those climate simulations, which include not just the natural forcing, but also the forcing due to greenhouse gases, which is called anthropogenic forcing. Now, when you look at this in further detail, we now know that the sun really contributes very little bit to the recent global warming that you have seen in the last couple of hundreds of years. It is primarily human-made anthropogenic causes due to the rapid emission of greenhouse gases, which you see here, the rapid rise in the greenhouse gases with time in the last 150 years, that is contributing to global climate change. Why is it important? It is important to understand this physically and to constrain what is the sun's contribution so that we can very clearly identify what are we and our activities contributing to climate change. So we can try and stop that or mitigate that. Okay, now we go to planets. The sun's activity also influences planetary atmospheres. And this happens because this high energy radiation from the sun, which is absorbed by the upper atmosphere of the Earth and of planets, energizes these particles in the upper atmosphere and increases their speed such that they're prone to escape the gravity of the planets. Okay. Now, there is also this steady stream of plasma material from the sun known as the solar wind, which also impacts the planetary atmospheres, especially when there is no magnetic field or magnetosphere of the planet to stop the charged particles. Okay, the magnetosphere acts as a shield. The Earth's magnetosphere, for example, acts as a shield or an umbrella that protects us from the solar storms and the solar wind. But for planets which does not have this invisible magnetic protection around it, which is known as the magnetosphere, they're prone to lose their atmosphere to this due to the strong radiation and winds from the sun. A marvelous case study is Mars. So Mars, when it was young, when it was about 1.5 billion years old, now it's about 4.5 billion years old. So much earlier, about 3 billion years back, it had a liquid iron core in its center, which was conducting, and conducting cores, if it rotates and there is convection, it can generate a magnetic field, which creates a magnetosphere around it. So Mars is thought to have a strong magnetosphere, which was strong enough to protect its atmosphere, shield its surface against this solar activity, and sustain an atmosphere where there was greenhouse effect, and therefore it had a warm, moist atmosphere, which is thought to be conducive to life. Okay, but we are exploring Mars only today, and today Mars does not have a magnetosphere. Mars lost its magnetosphere or magnetic field sometime in between, okay, because the liquid core froze, and now there is no motion in this conducting liquid core. The magnetic field disappeared, and it basically has very weak magnetic field. And today's Mars hardly has any sustained significant atmosphere. It's a very cool and very thin atmosphere, which is rich in carbon dioxide, and it's thought to be not conducive for life. In fact, we have not yet, in spite of many missions, discovered any evidence of life on the Martian surface, at least. And what this implies is this, that this interplay between the activity of the star, the ability of a planet to have a magnetosphere which can protect its atmosphere, plays an intricate role in determining whether planets can hold on to their atmosphere. For example, in Earth's case, is the oxygen-rich atmosphere that's very important to us, and whether we can breathe, whether we can sustain life in this kind of an atmosphere. So essentially, the changing activity of the sun and stars impact planetary atmospheres and the possibility of life in planets, which is known as habitability. Okay, and this is a very important and significant question, an area of very active research in all of astrophysics right now, where we are now hunting for exoplanets, which is planets outside the solar system, and trying to search for planets which are habitable, which may host life. And I'll come to the point of why this kind of activities are important, because you might think that we're wasting a lot of money in all these big missions, sending the satellites out, building these big telescopes, trying to find these tiny little planets very far away. What is the significance of it? You will know that at the end of my talk. Okay, so how do we explore the sun? Okay, so we realize that the sun is, something very important for us. How do we figure it out scientifically? Okay, there are various ways to do this. One of the ways to do that is to build a physical theory and then construct models of solar activity to understand how does the sun produce these magnetic fields, and how does this magnetic fields emerge out of the sun's surface and produce all these magnetic storms, sunspots. How does it accelerate the solar wind? How does it produce this strong, enhanced, high energy radiation? So for that, we build models to first of all understand how is the magnetic activity produced in the convection zone of the sun, the interaction of hot ionized plasma and magnetic fields. And you see a computer simulation that we have performed here, where we're seeing the birth and evolution of magnetic fields inside the sun. In fact, the models are now refined enough to be able to make predictions of the solar activity into the future. So here what you see is time and multiple solar cycles. These are past solar cycles. The black curve is the observed solar cycle. The red curve is what we have simulated in a computer. And you see a reasonable match between the simulations and the past observations. Based on this, we have forecasted the activity of the sun for the next 10 years or so, which tells us that the next cycle is going to be similar or slightly stronger to the previous solar cycle. So based on which we can conclude that the space environmental conditions, the frequency of solar storms, the solar wind conditions are going to be similar to the last 10 years. So just like you can predict weather on Earth, we are now taking the first steps to predict solar activity and the environment in space. When you look at the sun's outer atmosphere, this is an image, an observation from the SOHO satellite. No, it's not SOHO. This is a TRACE satellite. And what you see here are these very hot magnetic loops. And this is quite astounding because normally magnetic fields are invisible on the Earth, but due to various intricate physics coming together, the plasma associated with the magnetic loops in the sun gets heated, gets super hot and light up. And you can image them in extreme ultraviolet and X-rays. And this is an extreme ultraviolet image, which shows these beautiful magnetic loops in the sun's outer corona. And in these loops are born the magnetic storms that come out of the sun. Okay, so you can also theoretically model in a computer this magnetic fields of the sun's corona. When solar eclipses happen, it's a beautiful opportunity to image the sun's outer crown or the corona and compare your models, theoretical models, with the observations. So for example, here you see one of our simulations of the magnetic fields during solar eclipse, which was known as the Great American Solar Eclipse of I think it was 21st August 2017, where our models matched the observed corona that you see in the background, white color, pretty well. Now, this is very interesting. All of us are in this pandemic, the coronavirus pandemic. Where does this name coronavirus come from? What you see here is the solar corona. Okay, the outer atmosphere of the sun, which is known as the corona. What you see now is an observed image of the coronavirus, SARS-CoV-2. I show this to you again. This is the solar corona. This is the coronavirus. So essentially, now you know where this name coronavirus came from. It has come from the crown of the sun, or the atmosphere of the sun, known as the corona. This crown of the sun, or the atmosphere of the sun, the magnetic loops there can sometimes get destabilized and result in this very energetic magnetic storms. You see that the result of this magnetic storm is a vast amount of charged particles or plasma being thrown out. This is an actual observation. This is your sun, which you do not see from the Earth. This is what you see from satellites. When the storms travel through space, they are carrying a large amount of the sun's outer part, the corona, which is hot magnetized plasma, into space. And so these storms, the space storms, are known as coronal mass ejections. And sometimes they can come and impact Earth. This particular storm, there are two storms here, in fact, two coronal mass ejections occurred over the period of 2nd to 4th November. In fact, we dubbed one of them the Diwali solar storm because it impacted Earth on Diwali day, which is 4th November, and created this very strong geomagnetic storms and beautiful auroras all over high latitude countries, creating this beautiful sights, which, like, the images of which flooded the social media. When the storms come towards Earth, the storms and the magnetized plasma wind, they can have these adverse effects that I talked about on our satellites, on astronauts, on our atmosphere. How to study them physically? You can study them physically by modeling the interaction of this magnetized plasma from the sun with the Earth's magnetosphere. And you see that here, this is the Earth here, this tiny green bluish circle in the center, surrounded by an atmosphere. And then these white lines that you see are magnetic fields of the Earth. It is the Earth's magnetosphere. What you see is when the winds hit, the magnetized plasma winds from the sun hits the Earth's magnetosphere, the magnetic field of the Earth gets compressed here. When it gets compressed here, there is a region which is known as the bow shock. In that region, there is a sort of a surface called the magnetopause, where the solar wind is literally stopped. It cannot enter closer to the Earth. So this compressed magnetic fields of the Earth stops the solar wind and solar activity from moving in and impacting the Earth's atmosphere. And that is how we are safe. And that is why Mars is not safe, because the Mars planet has lost its magnetic fields. So it's very important for planets like Earth to sustain life, to have a magnetosphere, to be able to sustain the atmosphere against solar activity. And it's this theoretical computational models like this which helps us understand this intricate processes of how this sun-Earth interaction happens, leading to the possibility of life and habitability in planets such as Earth and beyond the solar system. We also observe the activity of the sun, and because the sun is the nearest star and has a strong impact on our technologies, advanced spacefaring nations like NASA, US, Japan, JAXA, European Space Agency, constituted of various European countries, have multiple satellites observing the sun and the space environment, which you see here. And in fact, India is going to launch its first space mission, the Aditya L1 space mission, which is still in development, to observe the activity of the sun, to understand how space weather originates in the sun, and also to monitor the near-Earth space environment so that we can establish how this magnetic storms and solar activity originate in the sun and then come and impact the near-Earth space environment. We are also planning to have one of the largest solar telescopes called the National Large Solar Telescope in India, which is a 2-meter class telescope, which will be situated in this beautiful region of Ladakh near Pangong Tso Lake. And this telescope will look at very high resolution the magnetic field structures within sunspots and look at this this structures to understand how solar storms are generated. How does this very hot corona depend on the magnetic fields, and how does the magnetic fields accelerate the solar charged particles and plasma winds? Okay, now I come to the end of our star. So every good thing has to end, and remember that the sun is sustained by the nuclear fusion reactions of hydrogen being converted into helium. But there is not infinite amount of hydrogen available. Eventually, the sun will run out of hydrogen. When that happens, the nuclear fusion reactions will stop, and there'll be a series of steps where the internal part of the star will collapse, and the outer part will expand out into a huge star, which will be called the red giant. This is the red giant phase of the sun. When it becomes a red giant, it will expand to pretty much double the size of the distance between the sun and the earth. So it will expand beyond the orbit of the earth, engulf earth, and move beyond, right? When this happens, the outer parts of the red giant is also being blown away, and conditions in the solar system will become extremely inhospitable. And you can imagine that the atmospheres of the planets will also be blown away when the star expands through the planets, right? So we lose the ability to host life. This is, of course, going to happen not now. This is going to happen far into the future at about 3.5, maybe 3 billion years from now. Okay. So at the end, what will remain is the inner part of this red giant will collapse and form what is known as a white dwarf. Very tiny little compact object at the center. And the outer part will be blown away in a form of a gas, which will be glowing in the light of this white dwarf, which really looks beautiful, but it really is a beautiful end. This is known as the planetary nebula. And you see this ring nebula, which is a separate nebula, image of this. I think this has been taken by the Hubble Space Telescope. This is how the solar system is also going to end. So what happens to life? Because the sun is now gone, we don't have the source of energy to sustain life. Probably the outer parts of the atmosphere has been blown away. Will humanity survive? It is very unlikely for humanity to survive in the solar system anymore. Okay. So what is the future beyond 7 billion years for humanity? Well, you hark back to science fiction now because you don't really know. You're in the domain of science fiction. And I don't know how many of you can remember this scene. This is from the movie Star Trek 4. Star Wars 4, called A New Hope. And what you see here is Luke Skywalker in a planet called Tatooine watching a double sunset. So our hope is then to leave planet Earth and find another habitable planet like perhaps Tatooine, which is in the domain of science fiction right now, but has to become reality if humanity has to continuously survive from today in planet Earth to beyond when the sun has died and become a white dwarf. And therein is the importance of trying to find habitable environments and planets far beyond our own, and to develop technologies to explore space and move far and further beyond Mars, the solar system, and explore the outer territories where someday we may find habitable conditions for re-establishing colonies for humanity. Okay, so I will summarize my talk now, and I hope that I have convinced you that what you thought to be an ordinary star displays extraordinary activity, which impacts many aspects of our life, including our modern day technologies. The sun also, on the one hand, sustains life. It gives us the light and the energy to sustain planetary climates and drive photosynthesis and establish life on Earth. On the other hand, if a planet loses a magnetosphere, solar activity can become a big hazard and blow away the atmosphere of planets, resulting in inhospitable conditions. So there is this beautiful interplay of physics, which determines how life can take form in a particular planet. And this depends on this astrophysical ecosystem, this environment of planets that we are in, and eventually on our parent star, which for us is the sun. And eventually, if humanity has to survive beyond billions of years after the sun is lost, we have to find another hospitable planet far away from here. And of course, this is all in the domain of research. We don't have answers to everything, but to understand our ultimate fate and to define our fate, we need to carry on doing the science that we have been discussing. I'll leave you with this last slide where you see one of the largest solar storms recorded. And on this, you see the Earth to scale. And you see that the Earth is a tiny little sphere in the overall scheme of things in the context of our parent star, the sun. And this tells you why our astrophysical environments, which is vast, and the activities of stars can have profound impacts on planets and the life that it hosts. All right, thank you very much.
Thank you, sir. I think it's time now for question answer session. So we'll take a couple of questions. Let us see from the chat box if there are some. Yes, sir. There's okay. Some simple question from Pritham. Why is the gravity works in this? Is the space-time has a relation, the curvature?
Why does gravity work?
Works. Is the space and time has a relation?
Okay, so gravity works because there is, if you look at Einstein's theory of general relativity, because there is a curvature in space, and any object which is massive will essentially curve the space around it more, which will create a sort of a potential for other masses around it to fall into or get trapped into. So this is why masses will be attracted. The impact on time is something that comes out of special relativity as well, is different from the attraction of the masses.
There's one more question. In fact, I just this is something maybe in the domain of fiction. Why people are not trying to become type 2 civilization so we could jump on other stars for survival of life? As you said, maybe whatever we are going to meet when the sun will not be there, so can we jump? I think some Star Wars kind of film they must have seen.
Right, Interstellar, I think.
Yeah, Interstellar, correct.
Yes. Well, so that is firmly in the domain of science fiction. There are no wormholes around. Okay. So and this big tunnels where this massive something space-time singularities where you can just jump into and disappear into another system. That doesn't work, right? What works is steady hard work, like building a planet, building a rocket, sending it out to 10 kilometers into the atmosphere. Take the learning from there, build a rocket, send it to the moon. Take the experience from there, take a bigger step and send human beings to Mars, right? This is incremental. Technologies usually does not jump in a way that you can reach from the moon to beyond the solar system. But if you look at what humans have achieved in the last 60, 70 years, from absolutely no space age, no rockets, to being able to go to the moon and back, right, is just actually amazing. And we have what? About 3 billion years more to go before we are seeing the end of the solar system, right? So if you're still there, if climate change doesn't get us, I think that is enough time for technology to advance to figure out how we can really get beyond the solar system in a more realistic way, right? And I think we have to pin our hopes in those more practical and real possibilities, not some magic.
There's another question from Salman Karim. It's can we control or take precautions for solar flares? Because you have seen some slides.
Yeah, so you obviously cannot control solar flares. I mean, look at the scale of events that you're seeing here, right? I mean, this is happening somewhere far away, and the scale of it is so big that you have absolutely no control on this, right? But can you take precautions? Yes. Remember that solar flares are not hazardous to human beings on Earth who are at the surface level, because the atmosphere is really absorbing the intense high energy radiation and most of the particles, right? So you're okay. Only when you are outside the Earth's atmosphere, you are susceptible. So astronauts are susceptible, satellites are susceptible to solar flares. So what we are doing now is we are translating this research in solar physics to operational space weather forecasting, where we are now actually forecasting the possibility of solar flares a few days in advance. Okay, once you have such kind of forecast, you can help prepare the satellites or help prepare for satellites being hit and errors in GPS navigation networks or telecommunications. You can prepare for that, right? In the sense, look at the equivalence of this and cyclones or heavy rainfall. Can you stop it? You cannot stop it. But you can, once you have advanced knowledge, you can prepare for it and reduce the, the, the harmful impact of such storms. Similarly, even in space science, we are working to reduce the harmful impacts of this massive flares and storms from the sun, but we will not be ever be able to stop them.
Okay. This, in fact, there are two questions almost similar. As you said, maybe from 3 billion years or more from now, there will not be, or mean, sun will not be there. So there are two questions on similar line. That can we create, maybe as you said, science will be much more advanced, or we can hope for that artificial light source and heat source, so that the Earth can we can survive on Earth.
Can we create an artificial source so that what?
Artificial source of light or heat, so that whatever we are getting from the sun, the same thing we can continue and still can survive when sun will not be there.
Well, so, okay. So even if one can in principle produce an artificial source of life, it is very doubtful that the inner planets will survive the red giant phase when the hot outer atmosphere of the sun has expanded as a red giant, because that atmosphere is going to engulf all the inner planets, including Earth, and go much beyond, right?
Yeah.
So we will not possibly survive that either. Now, can you have an artificial source? The artificial source has to depend on something on Earth, obviously. Maybe radioactivity or whatever it is. So you have to generate this, this nuclear reactors. So the resource is limited because you have this one little planet. How long can you sustain the needs with just resources from one planet? So maybe we need to go to other planets and find elements, radioactive elements, or other stuff that is important for us to survive. But keeping that aside, I do not think we'll survive the expansion of the sun into a red giant, which moves through the solar system and engulfs Earth. So you can take it pretty much for granted that life as we know it on Earth will not survive this phase.
Okay, Saket has requested, I think, he has asked question. I will read out. As we have observed, Professor Nandi, first time in 2010, that for 2 years, 2008 and 2009, the sunspots were mostly been missing. Why their absence for this long was there? That's one question.
Okay, so that's a nice question, and the answer is somewhat technical, but I will try not to make it very technical. In fact, we have a work on that particular aspect, explaining the unusual minimum of Science per Cycle 23. It was published in the journal Nature in 2011. So what we figured out is that this can result from a changing speed of this flow of plasma in the interior of the star, known as meridional circulation. So when you have a fast meridional circulation in one cycle and a slow meridional circulation in the early half of the next cycle, these two sunspot cycles get separated in time. And in between, you have a long sort of minima with no sunspots. And that we postulate to be one of the possible hypotheses for explaining this very unusual long minimum that we witnessed in 2008, 2009, when hardly any sunspots were seen.
There's another question. What is our preparation towards predicting more precise space weather?
Okay. As it stands currently, we are getting really good at predicting whether a magnetic structure on the sun will generate a flare or not. But we have absolutely no idea of when it will flare, in the sense, when will there be a storm. We can say that a certain region that I now observe, I can analyze it and say is going to flare in the next couple of days, but I cannot say exactly when. So that information, the research that is required for that ability is still ongoing, and we are not sure whether we can get there anytime soon. Second, once a solar flare has happened and a magnetic storm has initiated from the sun and is traveling through space, the next challenge is to predict whether it's going to hit Earth, and if yes, with what velocity and properties is it going to hit Earth? Because on that depends how effectively it can create geomagnetic storms. Okay, so I need a drink of water.
Yes.
Thank you. Okay, so that research is also something that is really an area of active research. We can do those forecasts, but they're large errors. The errors can be as much as like plus minus 12 hours in the arrival time of coronal mass ejections. And in terms of predicting the properties of the coronal mass ejections, we are still in the very early phase of research. So I would say that there's some things like solar flares, whether solar flares are going to happen or not, we can predict. But beyond that, everything is an area of active research. But remember that climate models, weather models, people started working on that in the 1950s. And now we have models which are matured, right? We didn't even know there was space weather 30 years back, 30, 40 years back, when we didn't have any satellites. Okay. We only came to know about space weather in the 1960s or later, right? And then we started worrying about it when we started sending satellites to host our telecommunication system, our GPS navigational networks, because now we are really dependent on satellites. So now we are worrying about the weather in space, right? So this impetus is also not there. So this is a very new and rapidly evolving field, space weather research. And we've hardly been at it for the last decade, couple of decades or so. So it's still going to take some time to mature to a level where we can be generating very accurate operational space weather forecasting, but we are trying. We're taking the first baby steps towards that.
Okay. I think I will take this last question because we are already now 5 minutes beyond our time. We have another program as well for audience. We will have live sky observation online with much better facilities now. So this question is from Chipra Sunil Morekar. The question is, Earth's magnetic field sphere was reported to have split and TIFR has recorded that. So is it possible to lose our magnetic field like Mars due to climate change?
No, climate change changes your atmosphere and the thermal properties of the atmosphere and the oceans. It will not impact the deep interior of the Earth, or the outer core particularly, where the motions of the liquid iron core is generating the magnetic fields. That is unlikely. What can happen is if somehow there is a meteorite impact or something like that, which completely alters the flow profile, or somehow if the temperature gradient in the core is lost and the convection stops, then we lose the magnetosphere. If you stop the Earth's rotation, you lose the magnetosphere. That can happen by a meteorite impact, which sort of imparts an angular momentum opposite to what the Earth has right now. So there's certain possibilities, but these are all extreme possibilities. And if you ask me whether one can predict if it is going to happen or not, we have no idea. Right now, here, we don't have any idea whether this is going to happen or not.
Okay, I think we will conclude it now because it's now, I think, 5:40 or just before that. So thank you, sir. Thank you very much for sparing time. In fact, I know we gave very little time to you, and you had very hectic when you mentioned that when I bothered you about the lecture summary so that we can give it to the press also, because sometimes people want to know what we are going to cover in the lecture. That help us. So thank you very much, sir, for sparing time and joining us on this very special occasion of ours, which is the 36th anniversary. So it will be, I'll tell you audience, those who have joined late maybe, or they had to go, this will be available on Facebook and YouTube as well. So you can, if you want to listen again, I think many things have been covered in this lecture. I have 2 pages of note. So it will be very difficult to summarize again. Again, it will become a lecture. But people should listen once again, maybe, to get more of it. And there are some questions also, some very interesting facts also being put up by Professor Nandi for all of us. And with this, that we know, as of now, whatever is there, the fate is very much clear from 3 billion. Even though it is 3 billion or more, but we cannot take it granted. We need to do some science. I think so many of his students are there who can be motivated for this and do something, so that many questions which have been raised, that what we can do, how we are going to do, make a rocket, go there or going to some other planet, all this to make it possible so that we can survive, like in Interstellar or Star Wars 4. Okay, so thank you very much for all the audience as well. And thank you, sir, our director, sir, also as well, for getting us connected with Professor Dibendu.
Yeah, thank you.
Thank you. Thank you very much, Mr. Chaudhary. Thank you, Mr. Mesh. All right, it was a pleasure. Bye-bye.